Hello, my name is Pfahler. I'm a master's student at University of Regensburg, and I will tell you something about mutual hazard networks and how we use low-ranked tensor formats to accelerate calculations involving this cancer progression model. In comprehensive cancer progression models, a large number of genomic events should be included. While mutual hazard networks model the progression using only d-squared parameters, the computational complexity to fit the model to given data scales exponentially in the number of events. This renders calculations using more than 25 events computationally infeasible. Using tensor trains, a low-ranked tensor format, this exponential complexity can be reduced to polynomial, allowing us to construct mutual hazard networks for a much higher number of events. We model a tumor as a d-dimensional vector, where each entry is 1 if the corresponding event is present and 0 if it is not. By assuming that events occur only one at a time, the number of possible transitions is greatly reduced. Additionally, we use the proportional hazard assumption to calculate transition rates, giving us a total of only d-squared parameters describing our model. They consist of the event's base rates and multiplicative influences between events. We store these parameters in the theta matrix and can fit a theta matrix to a given data distribution by optimizing the Kullback-Leibler divergence from the data. The calculation time of the Kullback-Leibler divergence and the gradients is now dominated by the solution time of two linear equations, which are exponentially sized in the number of events. Using the tensor train formalism, we are able to accelerate this process. In the tensor train format, a d-dimensional tensor can be approximated as a product of d three-dimensional tensors. The accuracy of this approximation is controlled by the representation's tensor train ranks. This reduces storage cost and still allows us to perform many important operations like addition or multiplication directly in the format. Because of this, the computational complexity of these operations is reduced from exponential to polynomial in the dimension of the original tensor. Most importantly, methods are available to solve linear equations in this format as well, while only scaling linear in the number of dimensions. Applying tensor trains to mutual hazard network calculations is possible, since the transition rate matrix can naturally be written as a tensor train, whose dimension and tensor train ranks is the number of events. Using this representation, we can calculate the time marginal probability distribution directly in the format. For evaluation of the gradients, the tensor train format can be used when considering each data point individually. Therefore, for both linear equations, the expected dependency on the number of dimensions is now polynomial and not exponential anymore. The speedup of this method can be seen best by looking at the runtime for one score and gradient evaluation. As we can see, the runtime of the standard approach scales exponentially with the number of events. For the tensor train calculations, we see that they require quite a bit of computational overhead for a small number of events, but depending on the accuracy of our calculation, we reach the point of break-even at around 20 events, and afterwards the tensor train calculation outperforms the standard approach significantly, allowing us to go up to 80 events. In comparison, the standard approach limits us to below 30 events. Of course, the accuracy of these results has to be assessed as well, since the tensor train format gives only an approximation of the true result. For this, we can look at the Kullback-Leibler divergence from the exact result to the tensor train approximation after a full optimization of the theta matrix. This shows that while the quality of the tensor train solution gets worse with growing event number, even at 22 events, the relative entropy between the two results is still only a tiny fraction of 1 bit. Additionally, we can see that the accuracy of the solution obtained through tensor trains is very well controlled through our choice of the maximum tensor train ranks. To summarize, we presented a mathematical method that enables mutual hazard networks to construct meaningful cancer progression models for a large number of events, and showed that the accuracy of the obtained results can be controlled as we need. This allows for mutual hazard networks to be applied to datasets with a larger number of genomic events, making it possible to discover new interactions between these events. With this, I'd like to thank you for listening to my Flash talk. Please visit me at my poster or send me an email if this talk sparked your interest.